Today it's my pleasure to have Desmond Pink. He's a Chief Science Officer of Nanostics from Canada. Dr. Pink is the lead scientist in the development of the Nanostics Clarity DX microflow cytometry platform. He has worked on the translation of liquid biopsy-derived EVs for more than 5 years, with a focus of identifying aggressive prostate cancer. And prior to being the CSO of Nanostics, he was the senior research scientist and project manager at Entos Pharmaceuticals and project manager with InnovaScreen. Today, he's going to share with us his study with title Building on an EV Diagnostic for Prostate Cancer using microflow cytometry and the lessons learned so far.
So thanks for having me, guys. I really appreciate being given the opportunity to just chat about what we've been doing for the last 2 years. Feels like 5 years, but 2 years in the diagnostic setting. So to start, I just want to disclose that I am a co-founder and employee of Nanostics, and I do take financial compensation. So I'm just going to start off. I'm going to sort of gauge this talk discussing some of the things about prostate cancer, but also more general ideas about developing a diagnostic using EVs. So for the work that we've been doing, the fundamental area that we're looking at is screening for prostate cancer causes unnecessary harm. That's the fundamental basis. And this is November, so this is Movember, and this is a month to actually reflect upon men's health. But for prostate cancer, screening basically involves looking at risk factors and symptoms, problems with urination, blood in the urine, your age, genetic susceptibility, but also your PSA that people get. And that's, that test is under scrutiny constantly, but also digital rectal exam. And looking at all of that, these are the criteria that are used to select patients to actually have a biopsy, but only about 15 to 25% of those actually have prostate cancer. So right off the bat, we're actually seeing so many unnecessary biopsies. Now, to truly diagnose prostate cancer, you have to have a biopsy. That's the only way to diagnose prostate cancer. And the biopsy there involves 12 needles, and I've got a little cartoon there. So you can actually see quite clearly that it's going to entail a lot of pain, discomfort, and chance of infection, and even life-threatening sepsis. The real problem is highlighted when you think about less than a quarter of the men diagnosed with prostate cancer actually stand to benefit from treatment. Most of these men actually have indolent disease that is not clinically significant. And you can basically live with that for the rest of your life. So what are we doing? So we've basically devised a platform technology to look at a signature derived from extracellular vesicles to predict disease within a liquid biopsy, whether that be urine, serum, plasma, whichever you have. And this cartoon basically highlights, we examine plasma or serum EVs from healthy or diseased patients. And these EVs are not purified. So you're having a mixture of exosomes, microvesicles, large oncosomes, what have you, whatever's in the mix. We then stain these for a variety of markers and characterize those responses by microflow cytometry. We look at then using a machine learning algorithm to identify a signature that is also related to healthy versus disease, but also aggressive disease. We combine that EV flow data with clinical data to generate a risk score. And the idea is that this risk score is what's going to be presented to the physician and the patient. And using that extra knowledge, the physician and the patient can make a more educated determination of whether or not to go for a biopsy. So using this, we're actually hoping that we can decrease the number of unnecessary biopsies. So how do you start developing a diagnostic EV test? So I thought about it, and then I was like, how did we start? Well, we didn't necessarily start the way that you traditionally would, but I would highlight that whether you're starting a diagnostic project or even an EV project in your lab, think before you execute, read as much as you can. And if you're trying to use a new technique, whether it be microflow, NTA, or any of the other techniques, reach out and ask somebody. ISAV is a great resource to come and actually find people that have been there and done that. So ask before you do something. It'll save you time, money, and frustration. Because at the end of the day, if you put in garbage data because you simply haven't processed your samples correctly, you might have a great model to actually define what the data could tell you, but you're going to wind up with garbage results. So I'm going to throw these little identifiers on the bottom. This is kind of my take-home messages for each of the slides. Highlighted with the orange yellow star. So this one, think, read, and ask before you execute a process. So before I jump into the microflow stuff, I talked to some of our co-developers that are helping us with this diagnostic development. And one of the things that, if you are thinking about building a diagnostic, you really need to figure out where in the whole process you are. So I've kind of numbered these from 1 through 9, and it basically goes from idea to invention to basically looking at proof of concept. And proof of concept goes under a number of scenarios, 0.3 to 0.6. And all of that is basically to show that you can do what you think you can under a bunch of different criteria. And then once you get to 7, 8, and 9, then you're actually at a point where you can actually begin some real testing to show that, okay, I have a diagnostic test that I can actually start looking at plasma or serum samples or urine samples from a patient and really start to get answers. But even number 7 is basically trying to find the environment in which to test. And what I mean is that you can't just do this in your lab. You have to put it in a situation where an actual diagnostic is going to be run. And we're very fortunate. We work with a company called Dynalive here in Edmonton, and they're a subsidiary of LabCorp. But this is a site where about, I think it's 20 to 30 million diagnostics are run each year, and everything from hematology to microbiology. So it's where all of the work is actually done. And once you walk into an environment like that, you start to realize that there's some differences from your lab. And one of the sort of big ones that you might notice is that there's not a ton of -80s around, or, not everyone is wearing lab coats is now in clinical gowns. It's just some of the sort of first things when you see there, and everything is automated. But then number 8 and 9 is basically now, does your technology work? Does it meet the operational requirements? And then at number 9 is where you finally start to make some money. Most times when I talk to people, when they approach us, they ask, how do you do this? Most people feel that they're in steps 7, 8, and 9, where actually they're probably in 2, 3, and 4. And it's one of those things where, reach out and talk to someone and actually just see what you need. And sometimes that can save you a lot of frustration and save you a lot of money. The other thing that comes in, and I'm going to get to some flow data shortly. One of the other things I want to share is that when you're building a diagnostic, it's not just the test. There are a lot of other things that you have to consider. The market evaluation is one that I'll touch upon. Just because you have a great idea and a great way to actually test something and get a good answer doesn't mean that there's actually a market for it. Safety. Sometimes, I'll give you a very easy example of that. We used to use sodium azide in our sheath fluid. Well, at the diagnostic lab, they don't allow sodium azide on site, so we had to switch to Proclin. And that's just another biocide. Staffing, that's a big one. A lot of these sites will be unionized, and you can't just go in and say, I need you to work an extra 3 hours. It takes time to actually do this. The points that I've highlighted here in orange are some of the ones that I'm going to talk about today. Other ones, if you want to reach out to me afterwards, I can highlight some of these. So given that there's 20 big criteria there, how do you do all of that? How do you accomplish this? Well, first off, you really need to have a good idea, right? It's got to be solid. Second, you've got to have a very strong, diverse team. And by that, I mean, you have to have a team that is willing to argue, but not take things personally. A team that's willing to look at problems and say, okay, that's a mountain I've got to scale. Well, we can't go around it. How do we figure out, how do we get over it? How do we do this? And you work together. You also have to accept that everybody has an opinion, good or bad. You have to accept it. And it's your responsibility to actually defend your opinion. Next, you need some significant cash flow. You need money. You're going to find that developing a diagnostic is going to take time. And for the first significant time period, you're just going to burn money. You're not going to actually be bringing any in. So if you can figure out some way to bring in cash, that's a bonus. Fourth is time to do everything. There is always not enough time. Something that you think should take a day is going to wind up taking a week. So you're going to need more of each of these. So now when you start thinking about what you have to do for microflow, there is a ton of pre-analytical considerations that you have to get into. I mean, think about what your design should be and how it's going to fit your long-term goals. What kind of platform do you want? How are you going to optimize and validate your data? For your samples, have you thought about doing a stability assay? And if you want to use fresh samples, have you figured out how you're actually going to get your samples from the clinic or wherever they're going to draw the blood or get saliva or whatever? How are you going to get those to the lab? Where are you going to get your cohort? What is your cohort going to look like? If you're building a diagnostic, for example, here in Canada, we don't necessarily have the ethnic diversity of the US. So we have to reach out to other sites to actually build upon that ethnic diversity so that we can actually get a better description of the population. Looking at your platform, you know, how versatile is it? How much does it cost? Does it have a big footprint? For example, one of the examples that was given to me a short while ago, this company came in to the diagnostic site, had a great test, great idea, things were going to work well, but the piece of equipment was about the size of a single room, and you essentially, in most situations, needed to build your hospital or facility around that. So they had to go back and rethink the entire idea. Think about your data acquisition. How well does your platform actually get data? What's your throughput? How reproducible are your data over a single day and basically over a year, 2 years? For diagnostics, you have to think about data storage, because some of this data has to be stored for about 25 years. How do you protect your data? Because of course you're dealing with patient data, which is very, very sensitive. So how do you protect it? Analyzing your data, there's a ton of software packages. I mean, you have to start realizing you're going to be looking at thousands of samples. So you're not going to sit there and draw an ROI or, you know, a region of interest or gate things every single sample. So how do you do this to get the throughput you need? There's a number of software packages. What kind of stats are you going to run? Can you batch? And then how are you going to communicate all of that to the physician, the patient, industry and quality controls like the FDA? How are you going to communicate all of that data? And when you sit down and look at all of this together, the thing that jumps out to me is that I still don't know what I don't know. And that's the scariest part of my day-to-day work. All right, so let's get into some of the meat of microflow. So this is a slide that always generates a lot of questions. You know, which is the best platform? Well, each of these platforms has different benefits and limitations. So how do you decide which is best for you? The one thing that I will say right off the top is just because you can see the smallest particle or resolve the smallest particle doesn't mean it's the best machine. The end user's got to decide which machine best suits the question that you're trying to answer. So to sort of put that in the summary, I kind of built this little table to show, you know, there's a lot of criteria, and each of these rows will have more details attached, maybe 5, 10 for each of them. Something as simple as the footprint. How big is this cytometer? If you're an academic, you may have a lot of lab space, and it doesn't make a difference if your cytometer is the size of a big microwave or needs to fit into a fume hood. For industry and diagnostic stuff, you know, we basically have to pay for all of our square footage that we're going to be using in the site. And some of that square footage could be $2,000, $3,000, $5,000 a month. So, you know, the smaller the footprint, the better. Performance. Performance is always a big one. Academics, you define what your own performance is. For industry and diagnostic, we essentially ask for IQ, OQ, PQ. So basically an installation and an operational qualification then also a performance qualification. And I'll get into that in the next slide. So something else to think about is software. So for some of the things that we get in academia, if we get a software update, sure, go ahead, just do it. For myself, if I get a software update, I need to make sure that nothing in that software update is going to compromise the data that I've already got. And it's not going to change anything that I'm going to get from now on. Automation. Yeah, if you can automate it, automate it. And usability. I know, like, if you go into a flow core, you get trained. But for us, once you get trained, you also have to pass competency testing on a regular basis, just to make sure that you're still operating the equipment in a competent, reliable manner, especially if there have been upgrades or some changes. And then also some of the equipment you buy is going to be RUO versus IVD designation. So RUO is research use only versus an in vitro diagnostic. And essentially that comes with, it could be the exact same piece of hardware, but a lot more paperwork to show traceability. So this platform checklist is basically what we call user needs. And it's basically what you can say, this is what I need an instrument to do. Well, after you do that, once you get an instrument, we'd like to perform a performance qualification to say, okay, I know what I asked the vendor to give me. Did the vendor actually provide what I wanted? So you do a performance qualification. This also helps you set up and define the limits and the ability of your machine to do what you want it to do. And here I've just basically highlighted some of the things I'll just hit on in the next few slides. Particle resolution, repeatability, carryover, coincidence, calibration, and some of these other ones I haven't put in. But these are things that I think if you're going to buy a piece of equipment that's $100,000, $200,000, it's a significant part of your operating budget, and it the vendor should be able to say, okay, you asked for this, this is how you test it. But at the end of the day, the onus is on you to actually do these tests. So for us, we're using the Apogee Micro GXP, or the Apogee GXP. So all of the data that I'm going to show you today was gathered on these. So one of the first things, because it's microflow cytometry, you got to be able to see small particles. So can the system resolve small particles from noise? And we basically set an acceptance criteria that we should be able to resolve small particles of defined sizes in the range of 80 to 1,000 nanometers across a refractive index of 1.38 to 159. So here I'm just showing the standard Apogee bead mix. So this is the 1527, which is a new version of the 1493s that everyone may know about, with the addition of an 80 nanometer polystyrene. So these can be resolved, but then you also want to go the extra mile and actually start resolving other products that may be out on the market. So these are the exometry beads. So the Vero 1A, which is a 189 nanometer, and the Vero 1B, which I believe is a 374. Now these are organosilica beads that have a refractive index similar to biological EVs. And that's important because polystyrene and silica scatter more light and show up at different areas than biological EVs when you base this on size. So looking at that, so just to give you an example. So in this peak right here, you see the black line. This is the 1300 nanometer silica, but it overlays on top of the 500 nanometer polystyrene, just to give you an idea. And if we put that, and I believe this is a 380 nanometer polystyrene particle here versus a 374 nanometer organosilica bead. But of course, those are beads. You also want to be able to look at biological particles. So these are the manufactured murine leukemia virus that Viral Flow Technologies has put out. I think Vera Tang is in attendance. So Vera, these are your viruses. So we like these. These are very clean. But again, now it comes down to stability. We can look at these and characterize a limit of detection, but they degrade over a week. So for us, this is great to be able to show right off the bat. We can actually see these. They're biological EV of a known size, 124 nanometers, and a refractive index that's less than 1.4. But over the course of a week, if I wanted to use these on a regular basis, I'd have to buy a significant batch. And these are some beads that we've developed in-house in conjunction with Apogee. So just showing the 83 nanometer polystyrene, some 100 and 120 nanometer silica and the 200 nanometer silica, so that we can actually see these, but also pull them apart. So that's great. You can see small particles, but now you also want to be able to show that you can get the same data repeatedly. So what we've done here is we're testing two things. We have an auto sampler attached to the platform. And I asked the question, can I actually get the same data if I run the same sample over and over again? So we did 4 runs over 4 days, 96 wells per run, and looked at both the total concentration of all particles, but we had also stained for one of our wells, and we have particles that are in the 405 channel, so they stain with a blue antibody. I'll just do that in a very general sense. A 488 positive and a 638 positive. Calculate the CVs for each of the runs, and then do a total CV. What this allows us to do is actually give an estimation of how well and how repeatable the machine is going to be. But we actually set an acceptance criteria that these CVs need to be 10% or less, and that gives us a pass. Because of course, if you're running these tests, you need to be able to say, is it a pass or a fail? One of the other things you want to be able to do is look at precision and accuracy. And I've just put this little cartoon here. So, you want your stuff to actually be very, very precise. You want to be able to hit the same bead size repeatedly. So to test this, we basically took the apogee beads. I believe this was the 14. Yeah, these are the 1493s. And this is the calibration lot 121. We run 10 or 12 sequential runs. So 2-minute assay. We run it at a particular flow rate. And then we look to see if we can get the same MFI of each of these beads in the same spot. And again, we set the acceptance criteria at less than 10%. And you can see here that we've got this. Doing the same thing, but on a multi-day. So now I'm looking at a different lot, but the 1493s again, looking at 30 runs over 30 days. And this is probably over 6 weeks, I would imagine. Now, this is what we use in the clinic. So this is a 45-second assay running at the same flow rate. We look at the same thing. Here we set our criteria at 15%, allowing for a little bit of drift. What you notice is that these big beads down on the bottom have a bit more variability, and they actually fail our criteria. So we had to go back and investigate why this was. What I realized was that some of these wells were actually sitting for 10, 15, 20 minutes before they got assayed. And if you plot the concentration of these beads over time, you find that the longer they sit, they actually settle out. So if I go back and actually run them in sits of 3, I can bring these CVs down to less than 10%. Accuracy is a bit harder to define. All I'm showing here are again the 1493 beads, but we basically looked at now what concentration did the vendor provide and how well did we hit that concentration. And actually we hit, in mean percent accuracy, we're actually about 95. Some of the beads are at 100. Some more a little bit lower, and sometimes this is how you set your gates, but you had to be able to go back and back it up. Now, if we wanted to do this with biological EVs, a bit of a reality check. The accuracy is more difficult to measure because you don't know how much your EVs are going to degrade or change over time. And I'll have a slide to show you some of that very shortly. One of the other things that the ISAV working groups are working hard on is to actually show people that you need to calibrate. So we've worked with Apogee to build a calibration, and this is especially important for setting up a diagnostic because you want to set up your settings on day 1. You don't want those to change. You need to have the same settings for your entire clinical trial. Otherwise, how are you going to say, the data is the same on day 1 versus day 100? And I've just shown you here, there's some breaks. This is a Christmas break back in 2019. And right here, this is the COVID interruption right back in February, and it spanned until early June when we finally were able to get the clinics back up and getting some patient samples. So this is a 5 bead calibration mix. So the thing is too, you can't just assume that your system is calibrated. And I think some systems will just say yes or no, it's calibrated. Go back in and actually check. Plot the data, get your Levy-Jennings and see how it looks. And sometimes you'll be surprised. Like back here, we realized that one of the bead populations was deteriorating. So we worked with Apogee and figured out what the cause was. And then we came back with an updated bead product. Now, it's also critical to realize that in order for us to actually run any patient samples, the system must pass calibration before anything is run. And if a problem occurs and the machine does not pass calibration and we go through our troubleshooting, I basically wind up going down, or one of my scientists, and we have to figure out what's going on before any samples can be run. Now, the other thing is to actually look at monitoring beads. So even though we have this graph showing, consistent data, we run the 1493s as monitoring beads, and we check fluorescent intensity and scattering. And you can see that same breaks, but we can see little points here where things were adjusted at a PM visit or preventative maintenance visit. And then with the new bead product, a little bit of a change. So all of these are checks and rechecks to make sure that the machines are performing how you want them to perform. And of course, calibration also means fluorescence. So we've been trying to get smaller and smaller beads to actually look at calibrating for fluorescence. And right now, this is an example of the 2-micron beads from Spherotech when I'm working with some of the smaller ones. And I had hoped to have that data available, but not quite there yet. Because we're working in a diagnostic setting, one of the most important criteria is to actually make sure that there's no carryover. No carryover basically means you want none of the previous sample that was assayed to get mixed in with the next sample that you're running. You don't want a positive sample getting mixed with a negative, or vice versa. You don't want that data to change. So to show that we weren't getting any of that, we basically ran increasing concentrations of, I believe this was plasma, and we did it in a 96 well plate. So we would run a sample of PBS, then a sample of plasma, sample of PBS, sample of plasma. The idea being that if there was any of the plasma carrying over, you would actually see an increase in the PBS wells. And these are the PBS wells down here. You can see that these aren't increasing as a flat line. Next to that, if you have a biological EV, and here we're using the palmitoylated GFP EVs. This was developed by Charles Lai a number of years ago, and we find that this sort of system, the palmitoylated GFP, is very, very stable, and we like using this for this type of assay. So we basically took these, put them in particular wells on a plate, and then looked at any carryover in PBS in between these plates. So this would just be basically a small diagram of the plate and the data presented as a heat map. Again, now looking at your spike concentration, this shows up as your bright greens, and this is the range right here. Now, of course, that's fine and dandy. This is a non-operational example. One of the other things that we do is we have a series of positive and negative controls. Following the positive and negative controls that we run each day, we have a well of PBS to actually check for carryover. And this is what this data is showing here. So for the biomarker that's in the 405 channel, 488 channel, or the 638 channel, we chase each of that with a PBS, and we check for any carryover there. And some of these events are actually fairly high. So basically our acceptance criteria is that there should not be anything higher than 0.1% of the previous sample signal in that PBS. And we look for that, or we actually go back if the sample comes back to the 200 or 400 events per second, which is reflective of PBS or the sheath fluid. One of the carry-on messages that I want to put here is that, even if you have carryover, that's fine. You have to figure out a way to get rid of the carryover. You have to understand it, understand where it comes from, but more importantly, how to fix it. For us, we know that with the Apogee platform, if we do a single wash, I can get carryover. If I do 2 washes, I don't get carryover. And a wash is not a PBS well, but it's actually a wash of the probe and the internal fluidics. One of the other things that we look at when we do our qualification is how much data do you need to have before that data can be considered reflective of the population. So of course, with microflow, you're looking at hundreds of thousands to millions of particles. So how long do you need to collect for? And some of the factors you need to look at would be flow rate, how bright is your fluorophore? Are you looking at rare events, or are you looking at a population that is very concentrated? So we developed an assay where we again used the palmitoylated GFP spike, We spike at 2 different concentrations in 2 different plates, obviously. But we then collect data for 5 seconds, 10, 15, 30, up to 2 minutes. And we ask the question, at what point does the 12 replicates for each time point, that the coefficient of variance comes down to 10% or less? And then at what point do the concentrations no longer change? At what point do you plateau? And we do that both for a high spike in the range of 3 to 4,000, and then also at a low spike in the range of 2 to 400 events per microliter. We do that at multiple flow rates, and then just assess the data. So, you know, the criteria would be a 10% CV for 5 to 45 seconds in certain instances. But also we look at the data using one-way ANOVAs. It's very simple stats, but it's very powerful. And we've shown that, you know, as you increase the flow rate, you can actually get more consistent data when the flow rates are a little bit higher than 0.75. Now, if you wanted to look at that same idea, but actually count what's the minimal number of events you have to count. So I think, you know, when I started doing flow cytometry, it was like the magic number was 10,000 events. But I think with EVs, because the samples that you utilize can be so variable in concentrations, you really need to figure out at what point do you start getting valid data. So in this particular system, what I've plotted here would be the number of detected events on the y-axis against the acquisition time up to 2 minutes. And again, look for the plateau and then ask, where do, you know, this plateau, and this is still based on the stats from the previous page, we're looking at between 300 and 465,000 events. Somewhere in this range is when that's the minimal number. So you choose a minimal number of events, and then I always like to give myself a cushion so that I'm, you know, if something happens, let's say we get a bubble or something, I can still collect more data and I still have a chance to get a valid sample. So I like to think of too, the time to valid data actually defines your assay throughput, because you have to look at the number of wells in your tests. You also have to look at how long it takes you to prepare and load samples, and then how long to aspirate and acquire the data. So that's the minimal number of events. So let's say it's a minute per well. Then you add on another couple of minutes to wash the system in between samples to avoid carryover. And then you have to ask the question, well, how many samples can I assay in an 8-hour shift or on a machine or per technologist? And then the time to analyze the data. So even though you may have a lot of throughput, you got to balance that with your assay validity as well. Coincidence or swarm is basically the range of valid sample concentration. So these are the range of sample concentrations in which you're going to get single particles going through the flow stream. So here, essentially what you're doing is you're going to take a sample, whether or not you probe with fluorophores, that's fine. But you're going to do a serial dilution of your unstained or stained samples, assay in the same manner that you're going to run your test. And for us, we trigger on scatter only. I like to test at multiple flow rates, and multiple flow rates gives you the available, you know, you get more points on the graph essentially. And for this one, we basically looked at, sorry, I just lost my train of thought. So you plot the mean intensity or the, you know, MFI, mean or median, I'll show you the median shortly, against the concentration events per second. And there are a number of ways to do this graph, but you want to look at the plateau of your fluorescence intensity. And that's kind of the valid range. As this goes up on the higher end, that's essentially swarming. You're now getting more than one particle going through your stream at one time. What I've got here in purple is the range of what the vendors define as the clean threshold for a machine. So 1 to 200 events. In the clinic, we give it a little bit more because we're running sometimes patient samples that are differently in swarm. And then this would be your single particle range in the green and red in the swarm. Plot this by your median intensity, and you find that things are compressed a little bit, and your range is now between 14,000 and 400. So now to put this into practice, and I've mentioned that, you know, as we run through things, we want to make sure that we actually have a clean system. So this is showing data over the last year and a half on one of our machines. The orange is basically the sheath. So our sheath has got to run sub 200 events per second. The diluent is got to run sub 200 events per second. And this is the daily check. If either of those event ranges surpasses 200 or 400 events per second, we have to go back and clean the machine again. When we run the samples, so we basically take all comers and we run the samples at a sit dilution. If we had to go back and actually run all of these samples to get a titration of sample concentration, that would mean an entire day lost. So your sample stability may be compromised, but also throughput is compromised and the cost of your assay goes up. So we've been very fortunate to find a nice range of valid samples. I've just shown here in the purple, the mean plus or minus the standard deviation. And we do have some samples in swarm, and you're going to get that in a clinical setting. Now, taking all this into account, you have to understand your process. And basically, you have to look at from the point of before you even get your samples, understanding the paperwork, ethics, what you're going to use, who you're going to use to ship your samples, how are you going to collect your samples, are you going to ship, how are you going to receive the samples, process and react, and then analyze. You have to identify areas that are going to cost a lot of money. Identify those areas that are going to increase the risk of your data being invalid, and identify those areas where you're going to get a lot of variability. Where are the points that are going to cause you big changes in your data? Are there any points in this process that are go or no-go for an entire test? Are there points that you can improve? And are there points in here or situations in this where you have no control? So shipping, you may be limited to one or two shippers, whether it be FedEx or one of the other shippers. Do you have a backup if those don't come? One of the things that we utilize a lot is quality and regulatory control. Of course, we're trying to go through the FDA, Canada, Health Canada, but also the EU regulations. So we're working towards all of that. And I won't go into any of those details, but what I want to comment on is that, quality control and development is huge. It's a lot of paperwork. There are a lot of right things and a lot of wrong ways of doing things. One of the things to keep in mind is that if you're coming from an academic background, it is going to mean a significant culture shift for your team. There's going to be significant time and money involved. There's going to be a lot of arguments because people are not going to want to do some of the things that they've never had to do before. And you're going to need consultants. Trust me, you can't figure this stuff out on your own. It is a logistical paperwork nightmare. One of the things that I like to challenge people with is, can you actually write an SOP or standard operating protocol for your test so that somebody can exactly replicate your data? And, a year ago, I would have said yes. And now for each step, there are so many ways that you can mess up an SOP because you're so used to actually doing the work yourself that you forget certain things. For flow cytometry, CLSI is coming out with their ways to test a variety of the flow cytometry applications. And I think the paperwork is H62. And CLSI is a set of guidelines that are put together from members of Health Canada, FDA, all the different countries that are going to have different regulations. They send over their experts to help, or the experts all get together to actually build sort of a conglomerate of regulations that should cover all of the different applications that you need to do, whether it's limit of detection, limit of blank, interference. So coming to that now, one of the next things you have to think about, and I don't think I have all that much time left, so I'll speed up the next few. Sample stability is critical. You need to look at, if you're using unprocessed blood, looking here, these are 3 common markers for platelets and EVs. If you don't process your blood for a number of hours, you're going to get significant changes. You need to be aware of that. If you're using, once you've figured out you're going to use blood fresh or frozen, you have to look at, well, what type of blood tube, what type of temperature are you going to ship at? Is it stable? So here we're looking at our 5 biomarkers, and this is a 48-hour stability assay. And we looked at 2 different tubes, EDTA versus serum SST. So it's the one that actually separates, it's got the plastic separator into it. And you actually have the tests, and we tested multiple temperatures for shipping. That allows you to say, my sample is stable for 2, 4, 3 days at this temperature. And that can actually make a big impact on how long you can assay samples. Once your samples are reacted, how stable are them? How stable are those samples? How stable are they at ambient temperature, at room temperature in the dark, or cold. Because you have to realize that in a lot of the clinical settings, the diagnostics, this is all done on the bench at room temperature. Please titrate. If you're using antibodies for everything, titrate. And I don't mean 2 or 3 dilutions. Do a full titration so you can actually get a good estimation of the stain index or the separation index. But also look at your median intensities. Actually track everything. Look at your concentration and your counts. Titrate when you get new antibodies. Titrate when you get new antibody lots or new antibody shipments of the same lot. Or if you've had a huge shipment and you want to test after prolonged storage. So if you buy enough and it's sitting in the fridge for 8 months, titrate it. Trust me, it'll pay off. Multiplexing. If you're going to do more than one antibody, you have to do your standard FMO control. Make sure there's no carryover or bleed into the other channels. And that's what we're doing. You're seeing here. The other critical point is to actually look at the order of your antibodies that you're using. The order of addition can make a huge impact. The single addition that you've got here, so this is what I'm calling baseline. This is what you're trying to achieve in all of your samples. Depending on the order, here I've just done biomarker 1, 2, and 3. And you can see in the first 2 situations, 50% reduction. Here in the green, this was completely decimated down to less than 10%. Same thing in the reds. So the order of addition can actually be critical. And here what I've called the trilogy premix is basically just mixing all of the antibodies together and adding them. The blue is elevated. The green biomarker was actually completely reduced, but the 638 was actually fairly stable. So your antibody addition is critical. So how does that play out over longitudinal analysis? So what I'm showing here is one of our biomarkers. It's a biomarker that has got a Cy5 attached. We need to confirm that each of our antibodies work every single day. So we've developed a series of positive and negative controls to test this. We've developed acceptance criteria to define when they pass and when they fail. And that's this dotted red line right here. And it's kind of a chicken and egg at the initial development of this, because you don't know how stable are your reagents, and you can't test reagent stability if you don't have a positive control that you know is stable for a significant amount of time, even if you freeze it, because freezing can actually have significant interactions and consequences for particular biomarkers. So here we're showing the MFI of the positive, concentration of the positive over time, and here's the negative over time. And these bright red ones, these are failures that we've had. These arrows down here are different aliquots of the antibody that we've actually put in, or the biomarker that we've put in. And again, these controls must pass every day before any patient samples are analyzed. So what are we doing next? Well, we're in the middle of a clinical study. Our interim analysis will be at 750 and again at 1,400 patients. We're now trying to increase our diversity, but COVID has really thrown a monkey wrench into our recruitment. We're just over 500 and some odd patients. We've now opened up sites in the US, Johns Hopkins, iSpecimen, and down in Florida. But of course, all of these have been delayed due to COVID. Logistics is hard. I'm going to tell you, shipping samples, whether it's from one town to the next or across international borders, especially if you have time and temperature restrictions. So we're now trying to automate. So one of the things that we've asked is actually how long can we run the same samples on our platform and actually get the same data? So what we've done here, we put 3 plates worth of sample into a deep well plate, and we just basically ran, I think it was 288 in this situation. I think we just basically ran out of time. We didn't want to come back on Saturday. In this situation, this is run number 2. We basically stopped in the middle, stopped the machine, cleaned it, recalibrated, and restarted the acquisition. And this is just with our Palm GFP spike into serum. Why did we do that? Well, we want to automate this. So this is the part that we're at right now. So we're looking at validation of, we're using the Opentron, so a very accessible liquid handler for the lab, basically do all of your reactions in there. And we figure if we can define a way to actually do our test in a $10,000 or cheaper liquid handler, this should be able to translate to any of the clinical liquid handlers, which have a significantly higher price tag, streamline our PQ for any of those. We've already defined our acceptance criteria, and we can do the testing for it. So that allows us to do, the validation, write the code, and also do the acceptable testing of the human versus machine testing. So what are the lessons we've learned? You're not where you think you are in development. Time, money, and sleep will disappear exponentially as you go through this. At some point, your team is going to need to balance business, time, practical realities of the testing, and you really need to be your harshest critic. You have to really criticize your own work to make sure it works. This is our team. So we got a very diverse team. We look at everything from the science. John finds the money. Robert actually does all of our machine learning, and we have an amazing team. My team is Diana and Michael, and they basically keep me sane all day. And of course, we couldn't do this with help from a whole bunch of people, getting our clinical samples from all of these guys. The Motorcycle Ride for Dad has been unbelievable champions of our cause. The university has been with us. We've worked really close with Apogee, and of course, we get funding from a variety of places. And with that, I'll say thank you. I'll take any questions.
Thanks, Desmond. That was very interesting.
Thank you.
Sorry, I know it was fast. It was a lot of data.
Well, it's an interesting, I mean, you basically described the whole process, which is something that academic labs are not necessarily aware of. So I learned a lot. And I have some questions, but let's see what's going on with the questions from the audience first. There is a question from Navneet Dogra. Yeah, you can go ahead. Hi.
Hello.
Hi, very good talk. So my question was that, do you see any differences in urine EVs versus blood EVs in the flow? Number of events are different, epitopes are different.
Yes. So one thing you have to realize is that there are a lot of things that can affect the concentration of EVs. So first and foremost, your diet. If you take, for example, with plasma or serum, FID versus FASTs, you're going to have a dramatic change in EVs. And if you say take first urine in the morning versus urines throughout the day, you could very well see significant changes. Will the epitopes be different? I'm gonna say yes. I've talked with other colleagues, and yes, a series of biomarkers that work in plasma may not work in serum. They may work in plasma.
Okay.
Then there is a question from Vera Tang.
Hey, Des, how's it going?
Not too bad, V.
So I was intrigued by your slide with the combination of antibodies.
Yeah.
Am I interpreting it correctly that in some cases you can actually get an increase in the signal above the single antibody?
Yep.
How's that happening?
I don't know if it's interaction with some of the antibodies. Some of these are full antibodies with FC receptors. I have seen it. I mean, some of these are also small volumes that we add in. The smallest volume that we add in is 3 microliters. So if we do use all calibrated pipettes, but if you do have a little drop on the outside, you may get a bit more.
Okay, I forgot. I don't remember what the scale is on the. It just looked like there was some that were like twice the height of the.
Yeah, and so I've seen this on, not just that one. I've seen it with a bunch of collaborator FMOs that we've done. It's definitely, there's something going on with the antibodies, whether they're coming together and increasing the binding, or you're changing the affinity. I'm not quite sure, but it's fairly regular.
That's intriguing.
Yeah, it's not one that I chase too much, just because it's such an involved assay.
Right, but I guess you guys regularly use 3 colors in your panel?
Yes. And these are all separated by, they're 405, 48, and 638.
Okay. And you don't see, I guess you pick an order where you don't see that strange occurrence.
Yes, for sure. And we do go back and test that. If we get new batches of the probe in, we go back and rerun the FMO.
Yeah, that's very interesting. I personally haven't noticed that in the academic setting, but I guess now I'm going to start paying attention.
It is one of the worst assays to set up because it is so many wells.
Yeah. I mean,
I think
sorry,
be aware too, like if you're using one patient, you may see patient differences as well. So you almost want to combine and do a pooled sample to negate that sometimes.
Okay, so you think it might be a patient-to-patient thing? It might be a sample thing?
It could very well be.
Okay, cool. Thanks.
Okay.
So we have a question from Jason.
Yes, hi, thank you.
Hey,
Hi, I very much enjoyed your talk. Thank you very much. I just had a question. I'm more interested on the clinical side about how you define, there was a lot of process information, but
yes.
I was interested in the prostate cancer, how you're defining high grade or aggressive disease and any accuracy metrics that you've had in your pilot studies.
So we started off, when we started this, we engaged the physicians and the urologists that were actually doing the biopsies. So the metrics here in Canada may be a little bit different than the metrics in the US and other countries. But right now for our clinical tests, we're looking at the new grading of, Gleason grade 2 and above, or aggressive cancer being Gleason grade 3 and above, as opposed to the older 3, 4, 4, 3.
Okay, thank you. And do you have any, I'm just curious how well your system discriminates in those grades.
So our previous test, we looked at an AUC. So when we did our pilot tests a while ago, our AUCs were 0.83. And right now we're just waiting for another couple hundred patients, and we'll do the interim testing and see how well we're doing. So one of the big things that we've changed is we're now using fresh plasma. So our fresh serum, and this is being built as a reflex test off of the PSA testing. So if a patient sample comes in, is screened as in the gray zone for PSA, I think here in Canada it's 3 to 10, then that automatically gets flagged for the Clarity DX.
Gotcha.
And then once we get that, we confirm using the biopsy data. And as we get the biopsy data, we're also following up in a longer term to get prostatectomy data to see how well the biopsy data matches with the prostatectomy. And then that'll really give you the trueness of your analysis.
Right. Thank you. Thank you very much.
You're welcome.
Desmond, I have a few questions. I have some curiosities. So first of all, you mentioned that that one important thing in this process is to change the culture of the team. What does that mean exactly? Can you elaborate a little bit?
So when you go from, how do I want to put this? So when we brought in our quality manager, every time I have a meeting with her and I say, this is how you do this, I believe that this antibody works this way. Her first question is, well, do you have the data to back that up? And it's basically, if you haven't written it down, it doesn't exist. Your SOPs, so for everything we do right now in the clinical study, every step of making an antibody, making a diluent, each of the steps are actually signed off on and initialized. And that's our traceability. That involves a lot more paperwork and a lot more time to actually do a test. To give an example, there's about 50 pages of paperwork that goes with each day's running of the Clarity DX right now. Once we get past that and goes into regular day usage, you won't have that, but everything has to be tracked. What I've seen,
but that should be the case also in academia, right? I mean,
yes, that should be the case, because what that does is that actually gives you your rigor and your reproducibility. It does. It's really difficult writing an SOP so that I can give you my SOP to make an antibody and a titration, and you should get the exact same. If I give you my antibodies, you should get the same data as what I get.
Right, exactly.
So
basically what you're saying is that it's even more strict than in academia.
Very much more,
It's really like indispensable. Yeah, no, I get it.
And I will back that up though, that what that paperwork does, though, if you do find that you have a problem, you now have a way to go back and track where that problem originated.
Oh, yeah.
Right. And that has actually borne fruit for us on a number of occasions where something has gone really strange and we realize that it could be someone saying a dilution is 1:1, or say 1 in 3. Well, is that 1 part plus 2 parts, or is it 1 part plus 3 parts? So we've actually been able to go back and actually check the volumes that they've added and be like, oh, okay, that's where the mistake was. And that's why this control was actually failing, because the working solution that day was made incorrectly.
Yeah. Okay. The other, I was wondering, you cannot anticipate anything about the prostate cancer results?
So here's the thing. I don't actually, so our team doesn't run any of the data. I see the day-to-day positive and negative controls. And it's one of these things where, like, I can't look at, I think in those, if you remember that slide where I had all of the green dots, we have over 5,000 or 6,000 samples run now, like individual wells and stuff like that. We actually use a machine learning algorithm to push it all through. And that's a balance of the clinical data and the flow data. And remember, you're looking at sometimes 1 million data points. So I can't look at 1 million data points for 5 different biomarkers, look at the singles, the doubles, the triples, if there are any, and give you an answer. That's where
but do you know if there is already, I mean, if the algorithm is working, if you have some candidate biomarkers?
Yeah, so we've got 5 candidate biomarkers that we're using. We've adopted this. So right now, we've actually translated all of our data from the academic lab where this was born down to DynaLife, which is the subsidiary of LabCorp. And we have 2 technologists that run all of our data. They make all of our reagents. They run all of the assays. They run the machines. They've been trained, and they do all of the troubleshooting. So if a major problem arises, then myself and my team go down. But other than that, it's hands off for us, because that's really putting your test to the test, right? You're now handing it off to someone. They're running it, and that's how you identify the problems. Does that answer your question?
Last question. Yeah, one last question is, do you think it's beneficial for somebody doing what you're trying to do to work in collaboration, for example, with the EV standardization committee of ISEV?
Yes.
For the flow cytometry in particular.
Yes. So I've talked with, anytime I get a chance to talk, myself and Vera talk all the time. Anybody that's developing a new standard, I try to get my hands on it. I've talked with Edwin a bunch of times about his particles. Anytime I can get a new sample, I try it, I run it, and basically, buying a new car, I kick the tires and see what happens to it.
Okay.
Dolores, can I ask a couple of questions? Yeah, sorry. Thank you, Desmond. Thank you, Dolores and Carolina, for organizing this. Desmond, so a couple of things. One, so this theoretically should be moved to the clinic, should be moved into the clinic. I've been trying to talk to the clinicians and say if they will ever think about having a facility like this in the clinics. But are you discouraging because it's really too?
No.
No.
So
okay.
Here in Alberta, we've been working with DynaLife, and DynaLife actually has opened up what they call a translational lab directly in the diagnostic center. So you walk into the center and you are there. And what they're saying is that, we have a lot of innovation in this province and in worldwide, but if you don't actually give the innovators a chance to put their tests into a real world setting, you're almost setting yourself up to fail, because you don't actually appreciate all the things you don't know. I mean, there's a lot more to this than just having a test and an idea. Can it work on the floor? And I can tell you, the 2 technologists that we have working with us have over 50 years combined experience. And when we give them something and they're like, this will not work, this will not fly.
Yeah.
It's a hard lesson. No,
it's
and
difficult.
if you give them an SOP that is not clear, they'll tell you.
That's right. So then the second thing, you probably follow up on Dolores' question. Those 5 markers, did I miss them? Did you mention them, or you haven't said?
So the only one that we've disclosed is PSMA. That's the only one that we've
PSMA,
disclosed.
yeah, I heard the PSMA. I didn't hear the other one. And the other person that, do you know, Jennifer Jones is working quite a bit. Okay, so is there something that you're doing different from what they're doing at NIH?
I couldn't tell you because I'm not sure what they're doing. I mean, Josh is there. Josh has seen this. He can probably tell you, but I'm not going to put him. I shouldn't put him on the spot like that because that's unfair.
Okay. No problem. Okay, no problem. Okay, very good. Thank you very much.
You're welcome.
Okay, that's it.
Along the lines, I'll ask. Lucia, Dolores.
Bye, Navneet.
When you bye, Lucia, still in office. Still in office.
Yes. I am gonna find the protesters outside. I'm a little bit scared, but we'll see. No, sorry, interrupt you. Go ahead.
No, when you capture your EVs, you don't care if they are microvesicles, exosomes, or whatever, right? That's also introduces.
Yeah. Sorry, go ahead. I've taken 2 tacks on this one. So up to now, I've personally not been convinced by the isolation techniques, because the thing that I really have to worry about is the variability. So if I take so it's the variability of the isolation techniques, then there's the the variability leads to a lack of reproducibility, but it also increases the cost of your test because you're bringing in another point. Plus, a lot of the other companies that we've talked with and different groups, depending on the type of test you're doing, the isolation is a no-brainer because it's money. You know, you have to ask, you know, how much more benefit is it going to bring to your test? And I'm not saying that it won't be there, and there are some groups that are using it very, very effectively. But for EV flow of this, I'm not convinced yet. I am testing something very, very soon, though.
Thanks.
Okay, Carolina, do you have any more questions?
Yeah, just have a quick question actually. Yes, so you mentioned about most people thinking that they're on stage 7, but they're actually probably stage 3. So I'm just wondering whether you can share what is the main thing that, you know, in your experience that, you know, we need to push through to go from stage 3 to the real stage 7.
It's really tough. I mean, we fell into it as well, but it is actually taking the time to go out and talk with the people who are actually, you know, you're not going to sell the test yourself. You're not going to develop an LDT and sell it out of your lab. You know, ideally you want to sell it to the Sonics or the Quests or the LabCorps of the world. Or there are hospitals that will do it as well. But then the amount of validation. So talk to someone who's been in the position and has been successful, or even like with us right now, we've hit a lot of the mountains. We're still hitting mountains. How do you get past it? Sometimes, you know, having a beer or a coffee and just chit chatting about your experiences will save you so much time and grief. The biggest one that I find right now is logistics. How are you going to ship your samples from point A to point B? I mean, I think there's a lot of things that people take for granted. You know, a lot of people just count EVs and say that that's the stability, but it's not. You know, it's the presentation of your biomarker of interest on that EV or within that EV. How stable is that?
How do you maintain like this, you know, standardized from different clinics and, you know, the collections and then the storage and shipment to your lab? I think that's actually quite complicated when you involve multiple numbers.
If you remember that picture at the very beginning, you had a picture of myself and my hair was a lot browner and a lot thicker. It is very, very hard. Even in those situations, you have to audit those processes. So we actually work with a group here called the Alberta Prostate Cancer Research Initiative. These are at 2 different sites within the province. They're 300 kilometers away. But even on a regular basis, we go down and audit the blood flow, the processing, the shipping, all of that. We've developed 7 or 8 different ways to actually ship fresh plasma, fresh serum, fresh urine on, you know, whether it be at ambient or room temperature. And I think if you can remember the slide that we had, we're actually shipping from Northern Canada up in the Yukon, as well as down in Florida. So we're looking at a temperature range of 80 degrees in the middle of winter. So -40 to +40, if you will. It's not easy. You have to accept that some samples aren't going to pass your acceptance criteria.
And actually, like, how many patients or how many samples needed until you actually go into the stage of marketable tests?
So that depends whether you're looking at a lab-derived test or if you want something from FDA. But you also have to go back then, and for prostate cancer, the number of biomarkers you look at times the I think it comes back to Jason's question, how well you actually diagnose the prostate cancer. So prostate cancer, the biopsies have about 25% variability in the actual grading score, right? And diagnosis is never actually absolute until you have, the variability of biopsy to prostatectomy. So you're only taking 12 cores, and they may not actually represent the whole of the disease process. So there's a 25% shifting there. I think on average, we've looked at it from here in Alberta. I think we've also looked at some of the Nashville samples with Andres. And that seems to be fairly common. So, all of those things affect, the end result.
Okay. Dolores, shall I close it? You good? Okay. Yeah. Thanks so much, Des, for the presentations. Learned so much from the industry side of view. And
thank you.
Yeah, we've got, a lot of discovery, but translational based research as well. And this gives a sort of a view of how we're supposed to progress from the discovery to the translational side of it. So thanks so much for sharing all that tips.